This little list we have here, it's going to make more sense once we actually go through perms and coms, because right now it's like, this is what a perm and a com is, but you haven't really learned it. So permutations and combinations. Permutations is when order matters, and combinations is when order doesn't matter. What does that mean? Well, a permutation is if you're taking something and the order in which you do it matters, then it's a perm. So for example, your PIN for your debit card. If your PIN is 1, 2, 3, 4, I would change it. But besides that fact, if it's 1, 2, 3, 4, and you put in 4, 3, 2, 1, are you getting into your bank account? No. So the order in which you put them in matters, right? Permutation. If you are going on a trip, a school trip, and in this class, there's 3 people who get to go on the trip, okay? So if you are first, second, or third picked, you get to go on the trip or you don't. So if you're fourth, you don't get to go on the trip. All right? So does the order in which you're first, second, and third picked matter? If you're picked first, second, or third, it might be like you might be a little more antsy by the time the third comes, but does it make it any more special? No. You get to go on the trip or not. So that's a combination, because the order you picked those 3 doesn't matter. However, if the 3 people who were picked had specific jobs on that trip, like one got to tell everyone what to do, and the other one got to eat whatever they want, and the third person got to clean up. Would it matter then if you were picked first, second, or third? Yes, then it would be a permutation. So if order matters in which you're picked, or in which you're picking things, then it's permutation. If order doesn't, a handshake is always going to be a combination, because your hands meet, you shake. Like, it's not the order in which you meet first doesn't make you any more special, okay? So we're going to go through the first thing, which is the fundamental counting principle. And the fundamental counting principle states that you consider a task made up of several stages. So if the number of choices for the first stage is A, or the first part, and the number of choices for the second stage is B, and the number of choices for the third stage is C, then the number of ways you can do the task is A times B times C. It's called the fundamental counting principle. So if we look at a toy manufacturer, it makes a wooden toy in 3 parts. So there's 3 parts to this toy. There's a top, there's a middle, and there's a bottom. Okay? So what we're going to do is we're going to do a tree diagram first. They want us to determine how many different colored toys can we make. So we're going to do a tree diagram first. We're going to follow along. We're going to pay close attention on how we do a tree diagram. Now, a tree often looks like vertical, right? These are actually horizontal. It expands with branches horizontally. Okay? What we do every single time when we go to do our tree diagram is we put part 1, part 2, part 3 along the top. Okay, not along the side, along the top, the different parts. You could put top, middle, bottom. It doesn't matter. Okay? Now what we're going to do is part 1 first. What options do we have for the part 1 for the top? We have red, white, blue, or pink, correct? So below that, we're going to list those. But make sure you leave spaces, because off of each of those letters, we're going to have, off each of those words, we're going to have branches. Okay? So we want to leave spaces. So we have red, white, blue, or pink. So I'm going to go red, white, leave a space, blue, pink. Okay? So those are the options for the top of this toy. Now, how many options do we have for part 2? Orange, purple, or black. So the middle of this toy could be orange, purple, or black. We agree? So we branch off of this. If the top was red, the middle could be orange. What was it? Purple and black? Could be orange, purple, or black. Okay? But that's not the only option, right? That was if the top was red. What if the top's white? Well, then we could have 3 options off of that. It could be white with an orange middle, or white with a purple middle, or white with a black middle. Or we could have blue with an orange middle, blue with a purple, blue with a black, or pink with an orange, or pink with a purple, or pink with a black. I'm going to run into problems with my branches here in a second. So that's just listing if it had 2 parts. We agree? But it actually has 3 parts. So what's the options for the bottom? Yellow or green? Yellow or green? So we could have yellow or green. So we could have a red top, orange middle, yellow bottom. Red top, orange middle, green bottom. Red top, purple middle, yellow bottom, green bottom. Drawing markers. Does that part make sense? How we came across it? So, how many different outcomes could they have? How could you count it? You could just count each one separately. So pink, black, green, pink, black, yellow, pink, purple, green, pink, purple, yellow. So we're technically just counting all these, right? The end part. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So there's 24 different toys. Now you feel like there's got to be a better way than having to list these out every single time. Because what if we added another part to this? There would just be more branches and craziness. So the fundamental counting principle stated that if you have different parts that make up a whole, you can take however many parts of this, multiply it by however many parts are in B, multiply it by how many parts are in C, or how many options. Correct? So we have part 1. So this is up here with the fundamental counting principle, I guess. We have part 1. We have part 2. We have part 3. How many options does part 1 have? 4. Part 2? Luke? Okay. The last one? 2. And it says that we multiply these. The reason why we multiply these is whenever you say and in between, you multiply. So I need this part and this part and this part to make the toy, do I not? If you say or, it makes no sense. I can have this part, or I could have this part, or I could have this part. So basically you could have just the bottom of it and you'd have the toy. Is that true? No, or it doesn't make sense. So you have to take this one and this one and this one. And when you multiply 4 times 3 times 2, you get 24 different toys. Okay, so the next example. A school cafeteria offers sandwiches made with fillings of ham, salami, cheese, or egg. So that's part 1. Fillings of ham, salami, cheese, or egg. The second part of this is it can be on white, whole wheat, or rye bread. Okay? How many different sandwiches can be made using only one filling and one type of bread? One filling and one type of bread. So you can use the fundamental counting principle if you're only taking one of each. If I wanted 2 fillings and one type of bread, I couldn't use the fundamental counting principle. Okay? So I would write in my notes, can only use FCP, fundamental counting principle, when taking one of each type. Okay? So we have different parts. So we're going to draw ourselves 2 lines because we have 2 parts. We're going to multiply them because it's the fundamental counting principle and because we need the filling and the bread. You can't have the filling or the bread. You just have bread or filling. Weird. Okay. So part 1, or the filling. How many options? 4. Thanks, guys. So many answers. And then bread? 3. Yay! Someone spoke. Okay. 4 times 3 is 12. So 12 different sandwiches. Okay. A Math 30 quiz consists of 8 multiple choice questions. So how many different questions are on this test? 8. And so each question would be its own blank because each question is a different part of the test, correct? So we're going to have how many blanks? 8. So this would be multiple choice. 1, 2, 3, 4, 5, 6, 7, 8. Now, each question has 4 choices, A, B, C, or D. So this option I'd have A, B, C, or D. So I list my options below, and above the line I put how many of them there are. So how many options do I have? 4. Then for multiple choice 2, I have A, B, C, or D. How many is that? 4. What about 3? And then 4, 4, 5, 4. So all of them have 4 options. And I need every question. So that's and. I'm going to multiply. Now some people will say, well, I could come up with an answer key to 8 multiple choice. What are the chances? They're pretty high. I could be able to come up with an answer key that matches it because it's only 8 questions. But this is 4 to the power of what? 8. What's 4 to the power of 8? Big number. How much is it? Is that what it is? 6, 5, 5, 3, 6? So you have a 1 in 65,536 chance of getting the correct answer key. I would study because that ain't happening. Okay? Now some people will say, well, how is that even possible? Like there's not even that many. But think about it. One outcome is just all A's. One of them would be all B's. One of them would be all C's. One of them would be all D's. And the next one could be 7 A's and a B. 7 A's and a C. 7 A's and a D. 6 A's and an A. Like there's a lot, right? A lot more than you think. Okay, what happens if we get restrictions? So this one didn't have any restrictions. Every single question I could get 4 answers. If I had said, though, that the first question could have to be the answer A, then I'm restricting it, right? So then it would only have 1 option in the first blank, correct? So that's what we're going to deal with. So here we have fundamental counting principle involving restrictions. When solving problems involving restrictions, it's important that the restrictions are dealt with first. You have to deal with the restrictions first. So if the first question had to be the answer A, you would have to deal with that first. All right? Okay. Example 4. In how many ways can 5 different models, it's very different here. It's very distinct that it has 5 different models. Now, why does that matter? Well, if you had 5 different models of cars that were black, and one was a Mustang and one was a Honda Civic, can you tell the difference even if they're exactly the same black? Yeah. So if I took 5 different models of cars and I lined them up, and they're all black, same black, and I tell you to close your eyes and cover your ears, and I move the cars around, can you tell that I moved them when you open your eyes? Yes. What happens though if they were all the same model? And I had 5 of the exact same black, same model car lined up. I told you to cover your eyes, close your ears, and I rearranged them and put them all back in the same spots, but different cars in the same spots, right? And you opened your eyes. What would you tell me? They're the same. Nothing's happened. Nothing's changed, right? That would be a repetition. We're not getting there right now, but it would be a repetition. Everyone say hi. They're in mute. The boys just peacing you. That's it. The girls are smiling. That's it. How many? 1, 2, 6. All right. Good times. Man, I was a little tired. Okay. So 5 different models. You could tell the difference between them, right? Same model, you wouldn't be able to. So that's why it's important. So you have 5 different models of black cars. So who cares if they're all black? You can still tell the difference. Great. 4 different models of red cars. How many cars total do I have here? 9. They can be parked next to each other in a parking garage. So I'm going to park 9 cars together, right? So I'm going to have how many blanks? 9. 9 blanks for like the parking spots, right? Now, if there was no restrictions other than I need to park the 9 cars, it would be easy. I would put 9 in this blank. Am I parking 9 cars on top of each other? Is that what that means? Like I'm stacking them? No. It means I have 9 options for this blank. But I park a car there. So how many options do I have for this blank? 8. Then I park a car there. So then 7. Park a car. 6. Park a car. 5. 4, 3, 2, 1. Okay? So if there was no restrictions, I would literally have 9, 8, 7, 6, 5, 4, 3, 2, 1. We agree? But there are restrictions, so I'm not going to have that. It says if a black car has to be in the first spot, so I need to have a black car in the first spot, and a red car has to be in the last spot. So I have to deal with those ones first. So, does it matter if I deal with the black or the red first? No, pick one. But it matters that you have to deal with those first, okay? So I have to have a black car in the first spot. How many black car options do I have? 5. Leaving a car there, right? So how many cars do I have left currently to park? In general, total. 8. I have 8 left to park, right? Because I parked 1. I had 5 options, but I left 1 there. Now the red one at the back, how many options? 4. Parking 1 there too, right? I left a red car there. I had 4 options of red cars to leave there, but I only leave 1. I had 5 options of black cars to leave here, but I only left 1. So how many cars do I currently have parked? 2. How many do I have left? 7. 7 to do the rest of the blanks, right? So now I can do them in any order because I'm done my restrictions. So here I have 7 cars to park. I park 1 there. How many do I have left for this one? 6. Park 1 there. 5. Leave 1 there. 4 left to park here. Leave 1 there. 3 left to park here. Leave 1 there. 2 left to park here. Leave 1 there. 1 left to park here. And I multiply them. Now, you could go 5 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times 4. And you will get a perfect answer, and it'd be great. But what I'm going to do instead is I'm going to go 20, because I'm going to put the 4 and the 5 together, because they don't kind of run in a run. They're not in a run, right? So I put the 5 and the 4 together. 5 times 4 is 20, and then this is in a run. It's 7, 6, 5, 4, 3, 2, 1. Correct? If that happens where you started a number and you multiply till you get to that 1, you can use the factorial symbol. There's a symbol in your calculator that stands for 7 and then all the numbers to 1. That's what the factorial symbol stands for. And it looks like an exclamation mark. So I can go 20 times 7 factorial. Now, if I did 100 factorial, that would be 100 times 99 times 98 times 97 times blah, 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 3 times 2 times 1, right? Every number all the way to 1. So you can only use this factorial symbol if you started a number and worked down by 1. Okay? Where the heck is that? So go to your calculator. We're going to go 20 times 7. Now, this is where you find the factorial symbol. You're going to press math. Then you're going to press left and get to probability. If you have the fancy calculators with color, you're going to press left twice. Okay? Until you get to probability. You need to be at PRB. And then you pick number 4. And then it does the math for you. Or I can prove to you. 20 times 7 times 6 times 5 times 4. Same number. Okay? So it just stops you from having to go 7 times 6 times 5 times 4 times 3 times 2 times 1. Or they might have just 20 times 7 factorial as your answer, like as an A, B, C, D answer. Okay? So we can park these 9 cars where I have to have a black first and a red last. 100,800 ways. Now, if I had no restrictions, I told you it was 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, correct? What's that? 9 math factorial. So no restrictions, I have 362,880 ways. So it's substantially less, which makes sense. The moment you throw restrictions into anything, you're going to have less chances or less possibilities, less outcomes. Okay? All right. The next question. Now, normally when we do math, we do a lot of like, I'll show you something and then you practice a whole bunch. But perms and coms are so different. Like they're all different styles of questions. So it's nice to see a whole bunch and then let you try them out and get stuck and ask questions. Okay? So we're going to look at example 5. Example 5 says, Eric has been assigned the task of determining how many odd 4-digit numbers there are. Okay? That's it. Odd 4-digit numbers. Well, we have to know what the heck that even means. How can you tell if a number is odd? A lot of people will say divisible by 2. That is true. It's divisible by 2. How else can you tell if a number is odd? What are the odd numbers? 1, 3, 5, 7, 9. Right? So you tell me if this number is odd or even. 23. 24. 25, 26, 27. What am I only changing? The last digit. Does it matter what the first digit was? Does it matter what any of the digits are in front of it? If I go 1,000,001, you tell me it's odd because of the 1 at the very back, right? So the way that we tell if something is odd is the last digit has to be odd. So if they say odd, we know last digit has to be odd. Okay? The last digit has to be odd. If it said even, then the last digit would have to be even, right? 0, 2, 4, 6, or 8. Now the last digit has to be 1, 3, 5, 7, 9. It can't be 11 because you're filling it into the last digit. Digit means one number, right? 11 is how many digits? 2. So we're only filling in single digit numbers. So 1, 3, 5, 7, 9. Okay? So they're not going to say odd, and by odd I mean the last digit needs to be odd. They're not going to tell you that. Them telling you it's odd is them giving you a restriction that the last number needs to be odd. Okay? The other thing is 4-digit number. 4-digit number means you have 4 digits, right? 4 blanks. 4-digit number would be like 1,000 or 1, 2, 3, 4. Is 0, 1, 2, 3, 4 a 4-digit number? Thanks, my friend. Is 0, 1, 2, 3, 4 a 4-digit number? If you're being paid by 4-digit numbers, would you accept a paycheck of 0, 1, 2, 3, 4, 1, 2, 3, 0, 1, 2, 3? Would you accept that as a paycheck? No, you'd say that's not a 4-digit number. That's a 3-digit number with a 0 in front of it. I do not want that paycheck. I want a 4-digit number paycheck. So $1,000 or 1, 2, 3, 4 would be okay. So what's the only thing the first digit can't be if you want a 4-digit number? 0, right? So if they say 4-digit number, they're actually telling you that the first digit cannot or can't be 0. They're not going to say the first digit can't be 0. They're going to say a 4-digit odd number. A 4-digit odd number means the first digit can't be 0 and the last digit needs to be odd. That's how they tell you it. Okay? So, does it say anything about our number can't repeat or anything like that? No. So we assume that we can repeat. The only way we assume we can't repeat is if it says you can't repeat. Okay? If it doesn't say you can't repeat, then you can. They don't say you can repeat. They just say nothing. All right? So we have a 4-digit number. We need to deal with our restrictions first. So that means the last digit and the first digit. Is there any restrictions on the middle digits? No. They can be anything. So let's go to the last digit first because I like dealing with the last digit. Below I list my outcomes. Above I list how many there are. Okay? So below, what are my options of numbers? Remember, the only options I have for numbers in these blanks are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Can't have 10, it's a 2-digit number. Just the 1-digit numbers. Okay? So my back digit has to be odd. So what are my odd numbers? 1, 3, 5, 7, and 9. Oh my goodness. Okay, 1, 3, 5, 7, 9. So I list my options below. How many is that? 5. So I put how many there are above. So I have 5 options of numbers that I could fill into that last blank. Then I have to go do the first blank because it's my other restriction. The only thing I can't have is 0. So I have 1 to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. How many options is that? 9. So I have 9 different numbers I could fill into this first blank. The middle blanks have no restrictions. So what could they be? 0 to 9. So I have 10 options, and I multiply them. So I have 4,500 4-digit numbers in the world. 4-digit odd numbers, sorry. There's 4,500 4-digit odd numbers in this entire world. So you always list the options below the blank and see how many there are above. Okay? Make sense? So Eric gets a bit more of a challenge. He's now been assigned the task of determining how many odd 4-digit numbers there are, but he can't repeat digits. So that means he can't, if there's a 1 in the back, he can't have a 1 in the first, second, or third digit. He cannot repeat. There's only one thing I change when it says I cannot repeat. I just pretend to hold numbers in places. So let's do the same thing. I'm going to go to the back first. I have 1, 3, 5, 7, 9. That didn't change. And that is 5 options. The only catch is when it says it doesn't repeat. I always make sure to circle a number and pretend I'm keeping it. So that when I go to list my options for the first blank, I don't list that number because it's being used. So 1, 3, 5, 7, or 9, you can pick any of those 5 to keep. It doesn't matter which one you do. Just know that whatever one you keep, you circle it, and now you can't list it as an option in the first blank or the second or the third because you kept it. I'm going to keep the 9 because I want to be able to list my numbers easier. You can keep the 1 too, it doesn't matter. Keep 3, 5, 7, 9. So now in the first blank, I'm going to list in the first blank all of the numbers that I can have. What can't I have in the first blank? 0. What also can't I have now because there's no repeating? 9, because I kept the 9. Had you kept the 3, then you couldn't have 0 and 3. If you kept the 5, you couldn't have 0 and 5, okay? Because we list our outcomes. So I'm pretending I'm keeping 9 here, and I can't have 0. So I have the options of 1, 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 options. So I put 8 above it. Because it's no repetition, I'm going to circle one of them. I'm going to pretend to keep the 1. Could I have kept the 2? The 4? Doesn't matter. Just keep a number so you can't list it in the next blank. All right? So a lot of people will tell me now I have 2 to 8. 2 to 8 is true. 2 to 8 is 7 options. And you'll pick 7, and then you'll pick 6, and then you'll circle that answer because it will be on your diploma, and it will be wrong. What other option do we still have that we didn't have to worry about? 0. We couldn't have a 0 back here because this is odd. We couldn't have a 0 here because it would make it a 3-digit number. So it's not like we kept it anywhere. We just didn't have a chance to even use it yet. So we still have it. So we have to put it here, which means we actually have 8 options, not 7, which is what you would pick, and that answer will be there. I promise you. Common error is putting a 7 there and forgetting the 0, because it's really easy to do, right? Now let's hold something there. I'm going to hold the 0 because it'll be easy to write again. So now I would have the numbers 2 to 8 left for here, and that would be 7. And what's 8 times 8 times 7 times 5? 2240? 2,240. So we went from having 4,500 odd 4-digit numbers to now having 2,240 just by making it that we can't repeat digits. So it knocks it down substantially, right? Okay. Car number plates in an African country consist of a letter other than I or O. So no I or O. How many letters are in the alphabet? 26. How many vowels? A, E, I, O, U. There's no sometimes Y. There's no sometimes Y. Beat you before you said it. Haha. So there's 5 vowels, correct? What's the opposite of a vowel? Consonant. A lot of people don't remember that word. Consonants are the opposite of a vowel, right? So if there's 5 vowels, there's 26 letters. How many consonants? 21. So vowels, we have 5. Consonants, we have 21. Letters, we have 26. Okay? So we know in the first blank can't be I or O. That's what it said. Then we follow by 3 digits. The first cannot be 0. So that one can't be a 0. No restrictions on the other 2. Does it say that they can't repeat those digits? Does it say that anywhere? Does it say they can't repeat the digits? No. It just says 3 digits. First cannot be 0. Doesn't say they can't repeat, does it? So fair game to repeat any of them if we want to. Because unless it says we can't, we can. Followed by any 2 letters which are not repeated. So these 2 letters can't repeat. Now, if this was an actual diploma style question, this is faulty. Because it doesn't say anything about, like, people can read into this 2 ways. Any 2 letters which are not repeated. So you could say, okay, these 2 letters are not repeated, or are they not repeated with the I and the O? What this one actually means is that the back 2 letters can't repeat each other. They have no correlation on whatever the heck the first letter is. So the first letter could be anything. It doesn't matter. Just these back 2 can't repeat. So can't end with like BB. Can't end with like CC. Okay? Nothing to do with this. So they would have to write the question better because I feel like it's not worded perfectly. Okay? So these can't repeat. So we have to deal with the restrictions first. So the first one can't be I or O. So how many options do we have left? 24. The second one, the digit can't be 0. So what digits do we have left? 1 to 9. How many options is that? 9. Then I'm going to go to the back two because those are also restrictions. They have to be 2 letters, which cannot repeat. So the first blank, how many options do I have? 26. You have A to Z. Then, because it says they can't repeat, I circle one of them because I'm holding it there. Then I would have A to Y, which is 25. Then those 2 middle green blanks just need to be digits. So is there any restriction on what those digits are? No. So they could be 0 to 9. They just have to be 1-digit numbers. So 10 and 10. It's a really large number. I think it's 14,040,000 or something. I think. Okay. Example 7. It says that James wants to travel from Pitland to St. Luke's, so from P to S. How many different routes are there from Pitland to St. Luke's? And remember, you're never going to like go back. You're not going to go Pitland to Q, back to Pitland, then to R, then back to Pitland. Like that is the weirdest. You're not going to ever do that route. No one would ever do that unless they were actually going from Pitland back to Pitland or something, right? They want to get to Pitland to St. Luke's, so we're always working towards it. So we could technically count these. This is 1, and this would be 2 ways, and this would be 3 ways, and this would be 4 ways, 5 ways, 6 ways. So there's 6 ways to get from Pitland to St. Luke's through Q, right? If we just counted them. Now, Pitland to St. Luke's through R. There's 1, 2, 3. Now, do we add them or multiply them? Remember, multiply means and add them means or. You're going to add. Why? Because you're not taking both. If you multiply them, you're saying you're taking these pathways and these pathways. That's a lot of pathways. You're taking everything. Which are you doing that? No, you're taking these or these. So it's 6 plus 3, which is 9. Is there any way I can do the fundamental counting principle to get me those numbers if I didn't want to add them all up and follow them along? Well, what can I multiply by to get me 6? Well, here I have 2. Here I have 3. I need to take these ones and these ones to get me to S. This one has 3. This one has 1. 3 times 1 is 3. And then add them. Okay. So you have 9. One last one and then some homework. The telephone numbers allocated in a rural area consist of one of the following. The digits 3, 4, 5. So we have the digits 3, 4, 5. Those are the only options for those blanks, right? 3 in the first one, 4 in the next one, 5 in the next one. Followed by any 3 further digits. Any restrictions on those digits? No. How many options do I have for the first blank? 1, it's a 3. Then 1, it has to be a 4. Then 1, it has to be a 5. Then these ones could be 0 to 9. There's no restrictions on them. Which is 1,000. Then it says or, and whenever we use the word or, we add. And, multiply, or add. And add sound like they should go together? They do not. And, multiply, or add. So we have a plus sign in between. And then we have the digit 2, followed by one of the digits 1 to 5, followed by any 3 further digits. So these could be 0 to 9. There's nothing stipulating on them that they have to be anything else. So 1 option, 5 options, 10, 10, 10, 10. So that's 5,000. And when you add them up, should be a plus sign, I guess. When you add 1,000 and 5,000, you get 6,000 different ones. Okay?